So what do you want to do? You want to watch the video on your
I don't know.
own?
Yeah, I'm gonna watch it on my own.
No, but he doesn't say anything. I mean, you don't need to see it. Um, did
But I
somebody?
can't hear it either.
You can't hear me?
I can't hear the video.
Oh, this is what you see?
Yeah, when I'm in the chat, then this is what I see.
No,
See
that's
this?
fine. I'm not because I'm not transmitting yet. So like now you should be able to see my stream. I mean the video that I'm watching.
Oh yeah, I can see it now. Yeah, I can
Yeah,
see it.
yeah, yeah, you shouldn't have an issue. Let me go to
Okay.
YouTube on my iPhone. La 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 la. La 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 la. All right, take two. Mm-hmm. Wait, is it running? Yes. All right, let's hear him.
Hey, crazies. Experience with physics has taught us that the universe is inherently local.
So can you hear him?
Yeah. Said
Okay.
the experience has taught us the universe is inherently local.
Mm-hmm.
Each point in space can only affect its immediate surroundings. So, influence at a distance must propagate through the intervening space. And that process is always limited by the speed of light. Or is it? Quantum entanglement might have something to say about this. Before we get into this, I should mention that this video is part of a big collab for World Quantum Day. But more on that later. Where do I begin? Everyone loves a good thought experiment. Imagine there's a high-energy photon. It's just minding its own business, traveling along. Then suddenly an atomic nucleus jumps out in front of it. The nerve...
So a photon is just light.
Okay.
Traveling along. Then suddenly an atomic nucleus jumps out in front of it. The nerve of some nuclei. Anyway, the interaction transforms the photon into an electron-positron pair.
So this is a normal electron, and this is a positron, which is just an electron with a positive charge. So have you ever heard of a positron?
Yes. Yep.
Okay.
So
There's
it
like
collided
electron,
with the...
neutron, positron, isn't
What?
there? Is there like electrons, neutrons, and positrons or something?
Positron is considered antimatter. So there's no free positrons in the universe. Usually, there's very few of them. So sometimes you can find a positron in nature, but very seldom. They don't. They don't last. There's much more matter in the universe than antimatter. There's many more negative electrons than positive electrons. And when they meet, they destroy each other. And there's just many more negative electrons than positive. So that's like nobody knows why, but that's just nature. So far, so good.
Yeah.
All right.
photon into an electron-positron pair. So it collided with the nucleus and broke apart? Well, no, at least not in the way you're probably thinking. This isn't like two objects being smashed together or something. Particles never really touch. Plus, it's not like this photon is made of an electron and a positron. They're not inside there. The photon just ceases to exist, and some of its properties are given to the new particles. Of course, energy must be conserved. Conservation of energy shall not be violated! Linear and angular momentum are also conserved, and the atomic nucleus helps with that.
So the photon was going straight to the right. So because of that, the positron is going a little bit upwards. The negative electron is going straight to the right, but the nucleus with which the photon collided is going a little bit down and to the right. So altogether, the linear momentum is the same as it was before. So before, did we lose someone?
No, someone joined. Hey, Blood Demon.
How are you guys?
Hey,
Good.
fantastic.
Oh, what's going on?
We're watching a YouTube video from the Science Asylum about how entanglement breaks the universe.
Whoa,
Yeah,
okay.
yeah. Anyway, so again,
Linear and angular momentum are
so before the photon was going straight to the right. So after, we expect altogether the entire system, the combination, the sum of the system must also be moving to the right.
also conserved, and the atomic nucleus helps with that.
So if we sum together all the arrows, you should get an arrow perfectly to the right. You see that this electron, the negative electron, is pointing a little bit upwards. But altogether, because the nucleus is so much more heavy than these two, so it pointing a little bit down is equal to both of these pointing a lot up. So far, so good. Hover,
What?
Okay.
are you watching? Are you listening?
Yep.
It's just what do you mean?
Do you have any questions?
I got distracted
You got distracted.
about. Yeah. What's the last thing you said about the?
The sum of the arrows from before and after. So before you had
Linear and angular momentum
a photon moving perfectly to the right,
Mhm.
and
are also
after
conserved, and the atomic nucleus helps.
you have a bunch of particles. Some of them are moving up and to the right, up and to the right, and down and to the right.
Can you tell me about
Okay.
a positron?
There's nothing to know. It's just it's a positive electron. It doesn't happen in nature. I mean, they happen very seldom in nature. It's not
Okay.
important. I mean, that's just the nature of reality. There's no question about that. Positrons exist in nature and in the lab. There's
I
nothing.
think quantum theory proves it.
What?
I think quantum theory proves positrons.
What? Well, I didn't repeat, please.
You know quantum theory?
Do I know quantum theory? No, just repeat what you said. I just didn't understand what you said. Can you
Yeah.
repeat what you said?
Uh, I think in my first year, my teachers taught me that a positron was proved by Einstein in quantum theory.
It's not important. I don't know. Positrons were postulated, I think, I don't remember, I think by Fermi. Fermi
Uh,
postulated
okay, let's skip
positrons.
it.
What?
Let's skip it. Get back to our main topic.
Yes, let's continue.
Helps with that. Yes, this particle pair, this electron and positron, are antiparticles, but they're so much more than that. They're entangled particles. Their
Okay, so the positron and the electron are entangled. Now he's going to explain how.
properties are linked. We know they must be opposite. If the electron is oriented up, the positron must be oriented down. If the electron is oriented down, the positron must be oriented up. They share a single state. It doesn't make sense to talk about them separately. But this is quantum mechanics, so those two states are not the only ones available. Say we don't know how either of them is oriented. The property is in.
Wait, Jove, are you watching? Are you listening?
Yes.
I'm just kind of listening. Yeah.
No, you have to be very focused. This is, it's going to get
Well, it's just a
very.
black screen for me, so I can't see anything. It's kind of
You can't see it?
no.
Mm, your screen is visible, bro.
What?
It's visible for me, at least.
Okay.
No, maybe it's a
Anyway,
mobile issue. I don't know.
all right. I don't know what basis states are, but what he's saying here is that either there's two options. Basically, there's two options. One is that the electron is spinning what we call up. That means like whatever. It's an up spin, and the positron is in a down spin, or the electron is in a down and the positron is in an up. Now you might wonder, but what about the rest of the possibilities? I mean, there's an infinite number of directions in which they can be spinning. I mean, they should be spinning in opposite directions, but why only up and down? Does anybody know the reason why it's only up and down?
Yes.
What's the answer?
Basically, this is not really, you're thinking of it as a top spinning in space. And what you need to think of it as when you do a measurement, it's either going to come out like north facing or south facing. It's going to be the measurement's going to be, it goes up or down from the measurement. So at any other given time, it's basically a mix of those states, and all other states are one of those two things. When you do a measurement, it's one or the other. And so when you say an electron is in the up state, you're saying there's a 100% chance of a measurement showing it would be in this upward state. And you would do this through, for example, a magnet. Like you pass the beam through a magnet, and you see that the electrons diffuse, like either go upwards or downwards, and that's where it actually comes from, right? It's been a long time since I've done this, like had this in class, but I believe this was, what is the Z experiment with this in it? Oh, it's totally off by, it's a weird shaped magnet that they put them through, and that's where they found the spin. So it's not that it's actually only those directions, it's that all other directions are made of a basis of those two.
Wait, I followed everything you said until the last couple of words. Please repeat the last.
So basically, if you say, for example,
Just
I want to
repeat-
have an electron with
you
a
just-
side spin. Right,
can
I'm
you
just going to
just-
repeat that. Yeah, just repeating that.
No, just repeat the last few words. You said everything else
So
is
all
combined.
others,
Mhm.
every other state, every other direction is basically a sum of those two states.
What do you mean by that? I don't know
Well,
what you just said.
that's why I was going to continue.
Mhm.
Right, so that's why I was going to continue speaking, which is that if you say, for example, I want to have an electron that's spinning in the like flat direction, so it's not up, it's not down, it's like horizontal direction in a sense.
Mhm.
You say, I want to have an electron spinning out. Well, that is equal to half up plus half down. So you'd say this electron is also you could break it into it's half up and half down, and now you have the direction of spinning it.
Okay. But I agree with you that I think this is the ket notation. That just means the measurement.
Yeah.
So either we measure, this is the measurement that the electron is up and positron down, or we'll measure.
No, electron up. Wait, electron up or electron down. I'm not sure I missed the part of why you're bringing in a positron into the system.
Because it's an entangled pair. So we created
Okay,
an
an
entangled
electron-positron pair.
Yeah.
All right.
So
Okay, so the reason you have one up and one down is the conservation of spin, basically.
yes.
Right, the photon had a quantity one spin going in, and so it has to, or is it zero? Photons have zero spin, right? 0 or 1. Let's say 0. So I believe they had zero spin, so you had to have positive 1/2 and negative 1/2 to have conservation of spin. Yes.
Right. Right. So according to this, in which way are we measuring?
I'm sorry, what do you mean? In which way are we measuring?
This implies a direction of measurement. You can tell.
Well, it's whatever. When you do your measurement, you'll have an answer. So,
but according
your measurement.
According to this diagram, according to this equation, where there's no equation yet, but according to this notation, in which way are we measuring? If we measure, right?
What do you, so you're saying words that you're saying words that I don't understand.
Mm-hmm.
Which way am I measuring is the kind of the weird thing.
So this says we're either going to measure the electron up and the positron down, or we're going to measure the electron down and the positron up. So in which direction are we measuring?
So whatever measurement you do, I'm sorry, I have to get off of this. Hold on, because you have an echo. All right, there we go. So I'm going to come back here. So when you do your measurement itself, the apparatus is trying to pick out an up or down.
Exactly.
So whatever,
Yeah.
right? So your apparatus is
Yes.
choosing up or down. Period. That's it.
Yes. So
your apparatus defines the up and down.
yes, and the apparatus is, what is the apparatus?
It's just a big magnet that you're
Yes.
passing the electron and positron through.
Yes, very good. Yeah, we're in
Right.
complete agreement. Very good. All right, let's continue.
Right.
What we call a superposition.
Okay.
Both parts
So what do you like? Yes. So that's what your apparatus is choosing, the up or down. And either you'll measure the positron down, which means the electron was up, or you'll measure the electron is down and the positron is up.
particles
Right. So now he's saying that we will either measure, I don't know why it's a negative sign. Shouldn't this be a positive? Like it's either this or this. I don't know why he says it's a negative. But what we have is 1 over the square root of 2 times this measurement, or 1 over the square root of 2 times this measurement. I think the reason is because he wants to have, we need to be able to say that altogether the probability should be 1. So 1 over the square root of 2 plus 1 over the square root of 2 is 2 over the square root of 2. And if you square,
Yeah, you get the probability amplitude once you square it.
but if you square 2 over the square root of 2, you get 4 over 2, which is 2. You don't get 1. And if you subtract, let's see what he says.
are showing an essence of upness and downness at the same time. Because, quantum particles can do that. They're still entangled.
Now, he says because quantum particles can do that. So he's talking about superposition. He says quantum particles can exemplify upness and downness at the same time, and that is what he calls superposition. He says because
Yes, we model the activity of the physical environment as two waves that can overlap each other, one of which describes the probability of being found in the up direction, one of which describes the probability of being found in the down direction, and the superposition gives us our answer to, if we do a measurement, we will find that. So I'm
But
just trying
listen-
to, it makes it a little easier if you don't say the particle is in this state of superposition, as opposed to we're modeling it as the superposition of two waves.
Well, guess what? That's exactly what the EPR paper is all about, and that is exactly what Bell's theorem comes to disprove. So you're taking Einstein's position, and everybody claims
No,
that.
no, I'm not. No, I'm not. I am not. That is not what I'm doing.
You said modeling,
Right.
but that's Einstein's position, no?
No. His position was that there's a set of variables that determine the outcome the entire time.
No.
There's basically a set of hidden variables that will give an answer.
You're going.
That was Einstein's opinion. There was a hidden variable, and what Bell's inequality proved is that there are no locally hidden variables.
But the purpose of the EPR paper had nothing. I mean, it used entanglement. It didn't come to talk about it. It wanted to resolve superposition. The purpose of the EPR paper was to resolve superposition, namely the upness and downness of a particle. Is it just our modeling, or is it the actualness? Are they really upness and are
That feels
they
like a bit more philosophy. That feels like more philosophy at that point. And so the point was, it doesn't matter. What can we model with it? And Bell's inequality shows we need to really treat them as waves. We can't assume there's a hidden variable that something else is doing things. So it's to say we're modeling it with waves is still fine. all we're saying is that there's nothing hidden below it.
I'm not sure what you're saying, but look at what he's saying. He's saying both particles are showing an essence of upness and downness at the same time.
Right.
But that's exactly what the EPR paper came to resolve. That's
But
exactly
it
what.
didn't, right? I mean, the point was it said if you do this measurement, you should find this, and Bell's inequality showed, see,
No.
they're wrong. It doesn't. It doesn't
No,
work that way.
everybody agrees you're gonna find upness or downness. Everybody agrees
When you measure.
when you measure.
Right, when you measure.
When you measure, everybody
Right.
agrees. The question is when you don't measure.
Right.
Is
So
the
the question
part?
is, what is a measurement?
Wait. The question is when you don't measure.
Right.
Is a particle in a superposition, or when you don't
Sure.
or when you don't measure, is your knowledge of the state of the particle in a superposition? What is the superposition?
What would be the difference? What would be the difference between those two
That's
statements?
exactly the EPR paper. The EPR paper comes to resolve.
Okay, what would be, I'm asking you, what is the difference between those two statements?
The difference is
Is it philosophical?
no, it's not philosophical. Of course not.
Then it's measurable. Then it's measurable, which is what the Bell's inequality demonstrated.
The difference, no. The EPR paper, first we need to go through the EPR paper. The EPR paper, we need to understand it first. The EPR paper presents a paradox similar to Schrodinger's cat. The EPR paper is Schrodinger's cat taken to the next step, because Schrodinger's cat, we cannot use Schrodinger's cat to resolve what is superposition. The question is, what is superposition? Is superposition our knowledge? Is it epistemological? Or is it the actual, as Nick from the Science Asylum says here, both particles are showing an essence of upness and downness at the same time. So the question is, and that's called, I think it's called ontological. So is superposition ontological, or is superposition epistemological?
So that's like, okay, this is exactly my point. That's a philosophical question.
But that's
and
fine.
it doesn't
I'm
have
not
fuck all to do.
disagreeing.
It doesn't have fuck all to do.
Yes,
right, but it doesn't have
it
fuck all to do
does.
with physics.
Yes, it does.
Not
That's
a bit.
that's the
Not one bit.
That's the EPR paper.
No, not one.
I heard
Not
you.
one bit. The EPR paper's problem is the faster than light part of it that seems like information's traveling faster than light. That's the concern there.
That's the proof. It's not a concern. It's a proof.
It's a concern. It's not a proof.
So what's
Hey, Maggie, get me a drink, would you?
What?
No, he's just hot miking or noise trolling, one or the other.
Oh, okay. Look, so the EPR paper comes to resolve. It comes to present a paradox similar to Schrodinger's cat. So Einstein and Schrodinger were arguing with Bohr. So Bohr said superposition is ontological, and Einstein...
Right. These are philosophy things. You're saying philosophical terms.
I agree.
You're saying philosophy terms. That's exactly right. Then it's not physics.
No, hold on. Okay, you've said this many times. Let's move on.
And you keep and then you keep saying it's not philosophy, and then you immediately start bringing up philosophical terms.
Okay, look, this is the EPR paper. Let's discuss it. I heard you.
Okay.
I heard you. Let's discuss it. I heard your position. I understand your position. I understand it.
Right.
It's understandable. But I think you're wrong. And the purpose of the EPR paper is to take Schrodinger's cat. You could argue that Schrodinger's cat is purely philosophical. So Einstein didn't like Schrodinger's cat because he didn't think that it doesn't create a paradox, a measurable paradox. So Einstein took Schrodinger's cat and he created the EPR paradox, which should be measurable. It
Right.
should.
It is measurable. We have done it. Yes, we have done it.
Okay. So what? So what did Einstein propose in the EPR paper? What's
So the EPR paper is if you take this, if you have this electron and positron coupled and you take the electron far away and measure it, you now know the outcome of the other experiment. And so the question is, how does the other experiment get affected by the measurement of that one particle? Because before you measure it, you don't know what's going to happen, and yet you measure it and you know one's up, and therefore you know the other one has to be down when it's measured. So the problem is, hey, where is this state being kept? Like, I don't understand how these systems are able to maintain state when it's just an electron. Where is that memory being kept? Either it has a memory or it's communicating at the time of the measurement. That was the statement. So the paradox is either it's faster than light communication, backwards in time communication. Any number of ways you can do this. It is problematic, or there's a variable that's keeping track of the state of this item, and therefore it's in. So Bell's inequality said there are no locally hidden variables. So we have to rule that out.
Wait.
That might be simple
Hold on.
distance, but we haven't ruled that in yet.
Wait. Hold
So
on.
that's kind of that's the paradox.
Okay, hold on. So that's too fast for me. So
Okay.
So the EPR paper proposes an experiment that is not supposed to be carried out. It's supposed to be a paradox.
No, the experiment can be carried out. It has been carried out, actually.
But when Einstein wrote the EPR paper, it's supposed to be a paradox, right? It's called the EPR paradox.
Well, no, it's called a paradox, but what it means is this thing happens and it seems conflicting with our other understanding of reality.
Right.
So the paradox is this event happens, we see it happen, we measure it happening, but it seems incongruent with our other understanding of reality. So it's not that the item can't be done, it's that our understanding of physics and measurements is incomplete.
Okay, slow down. For me. So when Einstein wrote the EPR paper, he thought that he settled it. He thought that superposition is settled. No one is ever going to bother him again. And indeed,
What? No.
Wait, Einstein went to his grave thinking he settled superposition.
I'm sorry, where is that quoted?
What do you mean? When
He
Einstein
thought he settled superposition? He didn't.
Yes.
He's pointing at a paradox. That doesn't mean he knew. If he's calling it the EPR paradox, it means he hasn't figured out what the answer is. So he
No.
hasn't solved it. He has
No.
pointed at a problem.
No.
Yes.
No. It's
Okay.
called proof. No, proof. It's proof by paradox. If you're able to.
No, there's no paradox. That's the thing. You keep saying proof by paradox. That works when you say, okay, it's raining outside and it's not raining. That's a paradox. It can't be both raining and not raining.
Okay.
See, therefore, you're just wrong. That's that kind of proof. This is not that. This is, hey, this is something that happens. We see this happen. We can measure it happening. We can't explain it with our current physical understanding. That's not a proof by paradox. That is a demonstration that our system is incomplete. Those are two different things. You're not saying the actual thing we measured doesn't happen. What you're saying is we can't explain why we're measuring this and it happens.
Okay.
That's what
Hold
they're
on.
saying.
Hold on.
So the fact it's called the EPR paradox means he couldn't explain it.
Okay. Hold on. Slow down. Okay. So the EPR paper that I never read. I
Proposed
tried.
hidden variables. Yeah.
Okay.
Proposed hidden variables.
It doesn't. We'll come back to it. Okay. Look. So the EPR paper comes to resolve superposition. Namely,
It comes to explain the issues with superposition.
No. I think the question was, again, is superposition ontological or epistemological? And The EPR paper comes to resolve this question once and for all. That's the purpose of the EPR paper. No?
I don't believe so.
So what is the purpose of the EPR paper?
The purpose of the EPR paper was to show, hey, when we do this measurement, we have so let me put it this way. Let's do a different experiment just for a little easier thought experiment. I'm going to give you a white ball and a black ball.
No, just tell me.
You're going to shake it. Wait, just hold up for a second. I'm going to shake them up, and you're going to reach in and grab a ball and then fly to the other side of the galaxy. And don't look at it. Just keep it in your hand, fly to the other side of the galaxy. Now, you fly to the other side of the galaxy, and I say, okay, in a million years, you open your hand and look at it, and I'll open my hand and look at it. Okay, so a million years later, you open your hand, and ta-da, there's a black ball in your hand. Now, immediately, you know what color the ball will be in my hand. It's immediate apparent that the ball will be white in my hand when that happens. So that's the, we've had instantaneous information from the other side of the galaxy go to you because you know what my answer is. Now, that's in a sense what the measurement of upness and downness is looking at. Now, in this case, it's very easy to understand. There's an underlying variable. The paint on the balls is the thing carrying the state of the ball. So we'd say, yes, one ball has a state of white paint on it, the other ball has a state of black paint on it, and that makes it very apparent what the memory of being kept of these balls is. The problem is, with an electron doing this, what's keeping this state of upness or downness? Because does it have it sitting in its state at the time? I thought these things were supposed to be independent. They're not supposed to have history of where they were before. I don't get it. What would make it prevalent from one to the other? Why don't we see a prevalence of electrons in all one direction or not? So that's kind of the question.
Rab Scuttle.
Yeah.
Okay.
Yes.
Rab Scuttle.
Yes.
Okay. I'll ask you again. So I don't know if you answered, but please try to answer in a short form. So the question is, what was the purpose of the EPR paper according to you?
To demonstrate there's possible faster than light communication if you don't have a hidden variable.
Okay. And all right, so you agree that this is a paradox, right? Or you disagree?
Well, when you say, what do you mean agree that it's a paradox? That's the kind of the weird wording there.
Isn't
right? So I need to know what you mean by the. I need to know what you mean by the word paradox.
Fine. So the question is, right? So I'm not the first one to say that there is an.
I know. Are you using word paradox as a synonym for contradiction?
Wait, one second. So my question is, you've heard the term EPR paradox, the EPR paradox, right?
Yes.
Okay. What is so?
I just said it 5 times. It's the apparent. It looks like you're having faster-light communication of 2 particles. That's what the EPR paradox is.
Okay. So so would you say that the EPR paper presented the EPR paradox?
Yes, it presented the fact that unless there's a hidden variable, you have faster-light communication, which seems problematic with our current understanding of general relativity and special relativity. So therefore, you either have faster-light communication or you have a hidden variable. So that's how you would have to resolve this. One of those 2 things.
Slow down. Please slow down. Try. Let's have
you
short.
told me to keep it short.
Yeah. Just answer short because you go on monologues and I lose you. I'm sorry.
All
right. So I'm just trying to nail you down as far as your understanding of the purpose of the EPR paper. So I'm just trying to nail you down.
The EPR paper was presenting the issue Okay.
I'm gonna nail you down. So if you monologue, you're gonna keep slipping.
Nail away.
If you keep monologuing, you're gonna keep slipping away, and I'm trying to nail you down. So I'm gonna need to
just start nailing.
Yeah, I need to cross-examine my witness.
Start nailing.
All right.
Just start nailing.
Okay. All right, cross-examine.
Let's go.
Okay. So what was the purpose would you say that the purpose of the EPR paper was to present the EPR paradox? Yes or no?
Yes.
Okay. So would you say that a paradox is
I didn't say that. Don't say I said that.
Hold on.
Don't say you say. You ask me questions.
Would
Don't
you-
rephrase it.
would
Just
you
ask me
say-
straight questions.
No, would you say that a paradox is a very good mathematical proof?
No.
Wait, what?
I
What?
said no.
What do you mean no?
You asked for a straight answer. I
Oh,
said no.
wait.
You just said no.
Okay. A paradox is not a good
what-
mathematical proof?
No.
What do you
No.
what do you think it's proving?
What is a
That's the thing,
paradox?
right? You're saying paradox. You're saying paradox, and you're using it. This is exactly what my point is. You think paradox is synonym for logical contradiction. If you ask me, is a proof by contradiction a good mathematical proof? My answer would be yes. You ask me if proof by paradoxes are apparent.
Okay.
That they appear to cause
Okay.
people's minds to not work
All
the
right.
way,
Got
but
it.
that doesn't mean it's a contradiction.
Witness. Hold on. You're my witness. Okay. Let's continue.
Okay.
Let's continue. All right. So I'm gonna good. So let's assume
The twin paradox is another. A twin paradox
No,
is
no, no.
another example.
Okay, no.
Right? There is a
You're my
resolution.
witness. You're my witness. So I need to.
Fair
cross-
enough.
I
Or
need
the
to
train
cross-ex-
paradox. Train paradox is a good one.
No.
There's
I
another
wanna.
one.
No, I wanna. No slipping
right.
away. I need to nail down my
ahead.
witness. Yeah.
Go ahead.
All right. So let's discuss this. Okay. So can we assume no faster than light communication? Yes or no?
If we assume that, so this is the kind of the problem. Can we assume it?
Wait.
Can we
I said yes,
yes,
but
we
you're
can
my
assume
witness.
it, yes.
Wait, you're my.
Fine,
Wait,
yes.
you're.
Yes.
Okay.
Fine. Yes, we
Okay.
can assume it. Yes.
Okay. All right. So, assuming that if we end up with faster than light communication, we get a paradox, right?
We get a contradiction.
Wait, a paradox.
A contradiction.
A contradiction.
In that case, if you say we assume X and we end up with not X, we have a contradiction. That's not a
Okay.
paradox at that point. That's a contradiction in our logic.
Fine. So if we end up with a contradiction, so one of our assumptions was incorrect.
Is wrong. Correct. Yes.
Okay.
Right.
And we assumed no faster than light. You agree to that?
Yes.
Okay. So that means what? What must the conclusion be therefore? Right? So
That's a yes or no question.
I mean, so we ran the entanglement. We had particle pairs. We measured one, and we always measure the opposite on the other, even at great distances. We instantly test the spins of both entangled particles.
Okay, now you're mixing up. Now you're mixing terms up. Be careful. You're messing up your terms.
Why? What did I mess up?
Okay, so when we measure one of them, we know the outcome of the other measurement. That is not the same as we've instantaneously. That's not the same as the words we've instantaneously measured both.
I'm the cross-examiner. You can later cross-examine me.
Okay, well,
right now, I'm cross-examining you.
No, I'm not going to cross-examine you. I'm just telling you you're using wrong words. But okay.
Wait, no, but
I'm just going to disagree with statements you make that are wrong. Then that's fine. You can cross-examine me. I'm just going to say no.
Wait a minute.
At that point,
Wait a
you're just
minute.
making wrong statements.
Given that we are measuring both particles at the same time, that's given.
We are not. No, it's not.
Wait, well, I'm cross-examining you.
Okay, no, it's not, you can't
okay,
do that.
Then the witness is refusing to answer my question.
You can't do,
then you're not my witness.
That doesn't happen.
Wait a minute.
So no, it doesn't happen.
Wait, what? Hold on. Are you going to answer my question?
I am. That doesn't happen. So no. When we do this, the answer is no. Can't do it.
This is second grade word problems. Given
Okay?
that we measure both particles at the same time. That's a given. You have to live with it. It's a hypothetical. Are you going to answer my question? Given,
Go ahead. It's a stupid hypothetical, but keep going.
No. Yes or no? Are you going to answer my hypothetical?
Sure.
Okay. So given that we measure both particles at the same time, and given that they always give opposite measurements.
When you said same time, relative to what relative to which reference frame, by the way, are you saying this?
A
Just out of curiosity.
center. It's good. A center referee. A center referee shoots a lightning.
So
The lightning goes.
Okay, so
both-
so just to be clear, you're at the rest frame of the two experiments, but you're not at a third measure that's like flying by.
Right.
So you are at the reference frame
moving.
of the two experiments.
No one is moving.
So if someone else is moving, they're going to not see them. So if someone else is moving, they're not going to see the measurements at the same time.
We sent two particles.
Just verifying that.
We sent two particles to the extreme ends of the visible universe, and we fired a laser beam from Earth. And when it reaches both measurers, they're going to each take a measurement and report.
Fair enough.
And they always report opposite spins.
Correct.
Therefore, is superposition ontological or epistemological?
Unknown. Doesn't matter.
Wait, no. This should settle it. No, you have.
No, it doesn't settle it at all. No, has no settlement. This has nothing to do with it.
So epistemological means that they were spinning in some direction that is opposite, and that's why the measurement is opposite. That's epistemological. That's Einstein's position. That's the EPR purpose of the paper, to prove epistemological superposition. If the superposition was ontological, then they could not communicate and they could not conspire to give opposite spins. This should have settled it. This is the purpose of the EPR paper. The purpose of the EPR paper was to settle superposition once and for all. Superposition is not ontological. It is purely epistemological. Yes or no?
That's the hidden variable hypothesis. That's the hidden variable hypothesis.
I don't care. I don't care about hidden variable.
No.
Wait.
No.
So wait. What was the answer? Yes
The
or no?
answer's no.
Wait.
No.
Wait.
No.
Wait.
No.
Wait. So
No.
no. Wait. So
No.
Okay. So my I'll repeat my question because it was a long question.
No.
And, wait,
I'm telling you the answer is no.
Hold on. Say no.
I told you when you asked nonsensical questions. I told you when you asked nonsensical questions, I'm just going to answer no.
Hold on. I heard you in the multitude of times that you said no. I heard each and every one of them. Now
Excellent.
Hold on. Now I want to figure out what did you answer no to? Because it was a long question.
It was a nonsensical question.
No.
It was the nonsensical part of your question, so I'm not answering it.
Are you saying no? Oh, you're refusing to answer the question.
Yes, because it's I told you when you ask nonsensical questions, my only possible answer is no.
Wait, you know is meaning you're refusing to answer the question?
You told me I have to answer one or the other. I told you, okay, in that case, if it's a nonsensical question, I'm only going to answer no.
What do you mean then? Okay, okay, let's go through the question again and point out the nonsense in the question. So I'm going to go through the question again.
Go for it.
So the purpose of the EPR paper was to demonstrate that superposition cannot be ontological. It must be epistemological. No. Okay. What do you mean no? No what?
No.
No what? So
That's
again,
not the purpose of
okay,
it. Was
I'll,
not
I'll
there's-
repeat. I'll
there was
repeat.
not the paper does not discuss epistemological or ontological aspects of it. That's not. It's not doing a philosophical paper there.
What do you mean
Right? That's not
philosophical?
his purpose.
What do you mean
It's
philosophical?
not
What do
doing
you mean?
philosophy. It's not
Wait,
doing.
wait,
That's.
wait,
It's
wait,
you're using two philosophical terms to describe a physics paper. It's not doing that.
wait. We're discussing a physical experiment, right? Given
Correct.
again. So given we created a particle pair spinning up and down, or as Bohr would say, in a superposition of upness and downness, as Nick says in this screen, both particles are showing an essence of upness and downness at the same time. So Nick from the Science Asylum takes Bohr's side without even knowing it. Okay. So I'm claiming that the purpose of the EPR paper is to settle superposition once and for all. Superposition is not ontological. The cat is not dead and alive at the same time. Rather, superposition is epistemological. Namely, it is our knowledge of the state of the particle that is the cat is both dead and alive in our minds before we measure it. So the EPR paper comes to resolve this issue by using entanglement, an entangled pair of particles. We send them each to the other side of the visible universe. We fire a lightning. They get the lightning. They conduct a measurement. They report, and they always report opposite spins. If superposition is ontological, then how did the two particles communicate faster than light? Therefore, superposition must be simply epistemological. Yes or no?
No.
That's not what
No,
the paper says.
Exactly.
That's
It
not what
doesn't
the
say
paper
that.
says.
Say that at all.
Did you read the paper?
Thank you, good boy. Yes, he's posted it.
Yeah,
He's posted a link in the chat and with the relevant paragraph that you're trying to describe. Thank you
Okay.
very much for that, good boy. By the way.
All right,
Yeah.
let's see.
It's like 4 pages long. I think not like a hard read.
Okay. So previously we proved that either one, the quantum mechanical description of reality given by the wave function is not complete, or two, when the operators corresponding to the two physical quantities do not commute, the two quantities cannot have simultaneous reality. This is not a hard read. Can you explain any of this?
Yeah, I mean that's
Go
pretty
ahead.
easy. Like
Go ahead. I'm listening.
yeah, it's saying so they have quantum mechanical wave function that they're all using for these calculations, and given the fact that these two operators don't commute on both sides, then
What
either
operators? Operators is the measurements? What is
operators are the mathematical you know,
the
whatever,
cats?
like plus and minus
Functions,
or like
mathematical
multiplication.
functions. Yeah, functions.
Okay.
Yeah,
The spins?
functions. Yeah.
They often represent measurements.
So the measurement of the spin, for example, is an operator?
Yes.
Yeah? Where is he? Hello?
Yes.
Where is he? Where's the guy that was speaking?
He might have a
What?
problem with the mic currently. Good boy. Yeah. Oh, he's there. He's asking you, is the measurement of a spin an operator? And I believe it's usually represented as an operator.
Mr. Good Boy, are you going to answer the question?
What's the question?
I'm trying to understand the word operator. Is that like the measurement of a spin? Is that an operator?
No, it's a mathematical function.
Well, what's an example of an... Okay, how would you map the measurement of the spin into the words that we're reading right now? where would it show up in this snippet that you sent us?
What difference does that make?
I'm
I'm just
trying.
giving you the
I'm trying to.
summary. I'm giving you the conclusion that they're drawing,
I'm trying
which
to.
has nothing to do with what you're saying.
I'm trying to understand. I mean, you're saying that the EPR paper has nothing to do with spins of particles. You cannot map the measurement of the spin of entangled particles into the EPR paper.
He didn't say that. He didn't say that.
I think he did. Oh, he said it doesn't matter.
No, I didn't say.
So can you?
I'm just saying, like I don't understand why you're asking this question.
I don't understand the
all
word.
I'm pointing out.
I don't.
All I'm pointing out is you said that the conclusion of this paper is to say either superposition is like ontological or it's epistemological,
Yes.
and that's not the conclusion of the paper.
Isn't that the purpose of the paper?
No.
Look, I'll read another portion of it. The elements of physical reality cannot be determined by a priori philosophical considerations, but must be found by an appeal to results of experiments and measurements. A comprehensive definition of reality is, however, unnecessary for our purpose. We shall be satisfied with the following criterion, which we regard as reasonable. If, in any way disturbing a system, we can predict with certainty, i.e., with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. It seems to us that this criterion, while far from exhausting all possible ways of recognizing physical reality, at least provides us with one such way whenever the conditions set down in it occur, regarded not as a necessary, but merely as a sufficient condition of reality. This criterion is in agreement with classical as well as quantum mechanical ideas of reality.
Okay, that just means locality, right? So
No.
the two
didn't mean any of that.
measurements, the two measurements cannot influence each other, right? Because they're too far apart. They're being conducted simultaneously.
I'm sorry. Did we listen to the same paragraph?
Yeah, can you
Because the last paragraph the good boy just read.
Can you
The last paragraph the good boy read just had nothing to do with that.
Can you post it, Mr. Goodboy?
Yeah. So I can't highlight and copy paste. I have to do images with these.
So you're not going to post the snippet?
He is
No, I
posting
am.
it. He's just saying it's going to be a copy. It's going to be a photo. So he's just taking a little time.
Oh, okay.
And he provided a link to the actual paper. You could just skim through it.
Yeah, the link's up there.
Okay, the elements of the physical reality cannot be determined by a priori philosophical considerations, but must be found by an appeal to results of experiments and measurements. A comprehensive definition of reality is, however, unnecessary for our purpose. We shall be satisfied with the following criterion, which we regard as reasonable. If, without any way disturbing a system, right, this means, right, it's too far. Right? This is the purpose of separating the two measurements so they cannot disturb each other, right? If without any way disturbing a system, we can predict with certainty, right? We can predict with certainty the spin based on one of them. As soon as one of them conducts the measurement, he knows the outcome of the other one.
You are adding an enormous number of words to that paragraph.
I'm
not sure
What
why.
are
The
you
word
guys talking
distance,
about?
the word, hold on, suffocating.
not.
So the word distance, for example, yes, the word distance doesn't appear in that. The word local doesn't appear in it.
I mean, but that's what it says here. If without any way disturbing, how can you accomplish without any way disturbing?
Look, let me back up. You're adding words.
Yeah, I'm
and
adding
now you're
words.
saying
Of
you're
course
not.
I'm adding
and you
words.
literally added, right?
Yeah, I
Don't
meant
add
that.
words to it. Just read it.
Okay.
You don't need to add words.
But look, what?
You can't say, I've added all these words and now this is what it says. You can move words around as much as you want. That doesn't mean that's what it said originally.
I'm not okay. Fine. Look, but to me, right? This is right, and the example that we set up, it's not even us, it's Bell, right? Bell brought up the experiment that we separate an entangled pair to separate sides of the visible universe, right? And this way, when one of them conducts the experiment, he knows with certainty, probability equal to unity, the value of a physical quantity without disturbing the other system because it's too far, and you can predict with certainty. This is exactly the case. I mean, it's an example. This is exactly what we're talking about. Then there exists an element of physical reality corresponding to this physical quantity. I don't know what that means. It seems to us that this criterion, while far from exhausting all possible ways of recognizing a physical reality, at least provides us with. I mean, but
Right. So that words, those words right there,
Mhm.
demonstrate this is not trying to do any ontological proof or epistemic proof. It's just saying, look, we can't tell you how reality works, but at least we know this little bit. It's that if we can predict a measurement and it's right, we at least know something about reality. That's all it's saying. It doesn't say we're in a simulation hypothesis. It doesn't answer the question,
didn't
is a
say-
solid system real? It doesn't answer any of that. It's not answering any of those philosophical questions. And for you to say it's obviously doing that
What's
is
the purpose?
disingenuous or just stupid.
No. What?
You just look, the fucking paper says it. It says it right there. It says it.
Why are you getting so upset? Jesus, hold on. What's the purpose of the paper?
Really? Do you need the abstract read aloud to you from this paper? Is that what we need to do? Do we just need to like? Is that the plan here? So like, I should just like read the abstract.
Why are you so upset? Jesus. Okay, in a complete.
So in complete.
Yeah,
In a complete theory, there is
let
an
me-
element corresponding to each element of reality. A sufficient condition for reality is physical quantity. It is possible for predicting with certainty without disturbing the system. In quantum mechanics, the case of two physical quantities, that is the right. This is what we're talking about. So there are two quantities that can have simultaneous reality. Consideration of the problem, making predictions concerning a system on the basis of measurements made on another system that had previously interacted with one results that if one is false, then two is also false. One is thus led to conclude that the description of reality as given by a wave function is not complete. That is the purpose of the paper. That's it. There. He's demonstrating the wave function does not have the complete understanding of the system. That's what he's trying to make the claim of. There. That's it. What's the purpose of the paper? That's the purpose of the paper.
Okay, you read too fast. Okay, so then either one.
The last sentence of the abstract. The last sentence of the abstract is
okay.
the purpose of the paper.
One is thus led to conclude that the description of reality as given by a wave function is not complete.
There. That's the purpose of the paper.
Yeah, I think the main struggle for like Einstein, for example, was like he wanted to maintain locality. So, you know, his whole thing was just like, well, look, we don't have the full answer, right? And like this makes it clear that like the wave function doesn't completely describe whatever is going on here, but he wanted very much so to hold on to locality because it was like integral to a lot of his theories.
And
But John Bell, you know, his whole like, from what I remember about the Bell theorem was that, you know, it basically if the experiments were to be carried out, which they were, it would essentially disprove at least hidden variables within locality.
Right, locally hidden variables. Yep.
Locally, yeah. So you could have hidden variables, but they would be non-local.
And that doesn't help Einstein either.
So when they say wave function, what do they mean by wave function?
They mean the model, for example, the Heisenberg's model or Schrodinger's model of the wave function that says, here's how we describe the location and the properties of an electron, or even Dirac's model that includes the charge and spin. And we say, this is our model for describing the wave function of an electron. And if we use that and do all this math with it, we can still get this, what is called the paradox of this non-locality part. And so the answer is, okay, that formula that you are using to describe these aspects of the electron is not complete. There's something else there that you are missing.
Let me
There
ask
must be
you.
something there.
Let me
that
ask
you're
you.
not taking
Let me.
into
Okay.
account.
Let me ask you a question. So you agree that we can, and this has been done, of course, we separate an entangled pair. They're far apart. We measure one. Really, in reality, we measure both at the same time, and both
No, we
simultaneously.
don't. No, we don't. We don't. Not in reality. We don't. That's the thing. You keep saying that. You're wrong.
They don't measure. They don't both measure. So how do
They
they
don't
know?
measure them both at this. They don't measure them both at the same time.
Then you could. Then if you give it enough time, you could claim that the information went from one to the other. You have to measure them at the same time in order to avoid.
No, you don't have to, because no, they're not avoiding anything. There's no purpose of saying at the same time. You keep adding those words. That's not part of this.
You have to
There's
do.
no at the same
If you
time
give
needed.
it, but
No,
if you
no,
give it,
because let me put it this way. Wait, hold on. So let's go to your reference frame. So pick reference frame that you're starting with, the laboratory reference frame, where you have the two measurement apparatuses are at rest relative to the laboratory reference frame, and you do them and you say, okay, when the clock strikes midnight, we're going to do the measurement of these two particles. Yes, then that reference frame we did at the same time. In the guy flying from from Alpha Centauri to Uranus, he's flying by at the speed of light, or near the speed of light, and he sees the left measurement happened well before the right measurement. And somebody else flying the other direction, a returning visitor from Uranus to Alpha Centauri, sees it the right apparatus measure first, and then the left apparatus. So the reference frame is going to change the order of operations, but it doesn't mean, and in either of those cases, you immediately know what the other answer is going to be, no matter what. And the point is, you instantaneously know what the answer of the other measurement is going to be. So you don't have to do the measurements at the same time. You just instantaneously know the result of the other measurement.
But if you agree that if I don't do the other measurement quickly, then then you end up with the possibility of slower than light communication, which everyone agrees is not a paradox, and then you ruin the experiment. So
right.
You have to
So
conduct.
my point is,
you have to conduct.
no.
Wait, hold on.
No,
I let you.
If it's on the other side, if it's on Mars, if it's on Mars, you can do it an hour apart.
Hold on, I let you speak freely. You don't let me speak even a little bit.
Because you keep saying the wrong things. If one's on Mars and one's on Earth, 1 hour apart would do it. Right? You could still do them 1 hour apart at the speed of light. That's too fast for the speed of light.
No, Mars and Earth is less than half an hour. It's half an hour, 27 minutes.
So half it. Okay, fine. Put it on Pluto.
Okay.
So one's on Pluto, one's on Pluto, one's on Earth, and now you can do it 2 hours apart for the measurement. That's still faster than the speed of light.
Sure.
Right. So
okay.
Like to my point, the instantaneous measurement doesn't matter.
Fine.
It doesn't fucking matter.
But
you want it in there.
But fine. Okay. Okay. So the purpose of the wave function in this discussion. What's the purpose of the wave function in this discussion? What is it?
Because they're pointing out, here's the wave function that everyone's using to model the electron. Here's what they're using to model it. And look, when we model it like this, we think there's something missing because of this thing we're showing you. So here's the case. You're using this thing to model it, and we're demonstrating there must be something missing because of this. So that's the purpose of saying wave function.
Okay, so then either one, the description of reality given by the wave function in quantum mechanics is not complete. That's Einstein's position. Or two, these two quantities cannot have simultaneous reality. What does that mean?
It means that like the answer is in that, like Einstein was saying, it can't be the case that these two measurements could be like coordinated together. He's saying it just can't happen. You couldn't do this. So he's basically trying to say the only answer is my hidden variables. That's what he's trying to say. And John Bell said, well, no, look, we've done the measurement. It kind of doesn't need that. So something else is afoot. And the really is going to come down to what is a measurement being like the big thing that physics never really, qualified, right? That's kind of the big open question is what do we mean by the word measurement, right? So that term right there is likely the key to solving all of this.
No, I mean, so what I discovered is in my research. So I just wrote a simple Python.
I'm sorry, your research that involved not reading a 4-page paper.
Stop. So I wrote a Python script. So if you disentangle, like if you run Bell's experiment, Bell's test on disentangled particles, do you know what percent you get? You know the percentage? Right?
I thought it was like 2/3 on each one of those. It's been a while. But you just do this mathematically. Why did you write a Python script to do this?
I like testing things.
But this isn't a test. This is not that you just wrote a script that did the math when you could have just done the math.
Yeah, I'd rather run the script.
Well, the math is already solved. Why would you run it?
I mean, obviously the different people are giving different results. I mean, you have.
Well, but you're doing it with a program, not with reality. You're not running an actual test that's trying to split a beam and do the measurement. You're writing a simulation, and the simulation will give out whatever result you want it to.
Exactly.
Right, but the simulation is going to do what you told it to do.
Yes.
So it's not fucking simulation. It has nothing to do with reality. Your Python script is bullshit.
Let me ask you a question. If you run Bell's test with the 0, 120...
In reality?
Yes, if you run Bell's test...
In reality, not on a script, but on an actual reality thing.
Okay,
continue.
On disentangled particles, what do you get?
When you run Bell's test, and this is like spin up, spin down on that, I'd have to go back and read the test. But if I'm just measuring, I'm going to have, if nothing's entangled, it's going to be 50% chance up, 50% chance down.
What is it?
50% up, 50% down. For example, on just electron, it's just random.
So what's the difference?
There's no preference.
Right. So what's
it would be before Bell's test.
Yeah.
Because Bell's test adds, I think, a third angle of deflection or something. And so you expect to get a certain percentage of particles that constitute a wave pattern or whatever. And it turns out that you get something completely different.
Hold on. Let me ask again. So if you run Bell's test on disentangled particles, what do you get? What's the percent up and down, whatever? What's the output?
I'd have to go look up the test, right? I haven't looked at this test. So why don't you describe the test to us that you're trying to simulate?
Oh, it's just so you take two particles that are disentangled, they have nothing to do with each other. You send them to each apparatus. The apparatus selects randomly.
Stern-Gerlach device.
Yeah, Stern-Gerlach selects randomly in real time 0 degrees or 120 degrees or 240 degrees.
Okay.
What?
That's okay.
What?
Selects randomly in real time. Those words are just so painful.
Yeah, but that's exactly what Clauser and whatever.
It's not selecting randomly in real time.
Yes,
it's not like real time has nothing to do with that phrase. It's not selecting randomly.
Well, it's supposed to, it's supposed to be They connected it literally to stars. The starlight determines the randomness of the selection of the angle of the measurement of
Ah,
each
ah.
apparatus.
Boy, these were like you. You really need to do some more research on this because your words are just horrible.
Like what? What did I say?
Okay, the apparatus is not selecting randomly. The apparatus
using-
is showing the measurement. No, the apparatus is showing that when it does a measurement, there's no preference of one direction over another.
No. There's videos about this, exactly how they did it. So they connected a telescope to literally to remote stars that are millions or whatever light years away.
Yeah. They're trying to get photons so they knew we're not interacting with each other, right?
And that's the determination of the angle of one of the three angles, 0, 120, or 240. So they had as random as possible.
No, what are you
selection.
talking about? They're like these words. No,
No?
no,
No what?
this is a bizarre phrase you're saying.
Why?
As random as like you. Okay, the wording you're saying makes it feel like the star. Like what you're describing is the tool. This Stern Gerlach device has a little knob on it, and it's looking at Starlight and then choosing. Okay, that one's at 120. Okay, make it come out 120. All right, the next one's at 240. Now we're back to 120, and there's a little knob that's flicking around to make the spin or whatever come out in that answer. That's not what fucking happening.
Not to make the spin, to make the angle of measurement, to determine the angle of measurement of the apparatus. No, I'm asking. That's what I understood. I mean,
No.
physics girl made a video about it. She interviewed. I think she
Okay,
interviewed.
okay. I believe she did. I don't believe you understood anything she said.
She interviewed the guy. She
I
interviewed
understand
him.
she did this. I hear you. I'm not doubting her research or that guy speaking. I'm doubting your interpretation.
What? Then you tell me. Well, I don't care either way. What do I care? I'm not. I don't have a dog in this fight.
Yeah. Yes, you do. You're
What?
questioning the witness. You're putting up. You're saying what it's going for. You're actually You're running the room with. Here's what we're talking about. How could you say you don't have a dog in this fight when you're fighting the dog?
I don't care. I don't care. What? Look. Whatever the look. Whatever the answer will be, will be. Well, I'm not gonna lie that the answer. I'm not gonna give you a false description of reality. I'm not gonna lie. I'm not here to. I can't make money. I'm not here making money from Einstein or Bohr winning. I don't have money on Bohr or Einstein. I don't have a dog in the fight. My preference, of course, is simple. What you see is what you get. That's my preference. But if I end up like I'm trying to figure this out, I'm trying to make sense of this universe. Einstein seems to be the sensible universe. So if you show me evidence, are you there? Oh, he's gone? Wait, he left? Everyone? Okay. Who wants to talk? I'm hungry. This was a good conversation. Finally, I'm able to talk to people who actually understand this material. This is one of my very first discussions, my very first actual debates with knowledgeable people. I've been doing this for months. Every time people tell me, no, you're too dumb, we're not going to debate you. And now this guy left early. Good boy, are you listening? Good boy.
Yeah.
What do you think? What's going on?
I mean, hold on, sorry, I'm just taking care of my kid. I don't really know what the exact contention you have is with Bell.
With Bell? I mean, I'm first on the EPR. I'm first trying to understand the EPR. I mean, yeah, I'm also trying to understand Bell. What my contention with Bell is, my intuition is that there's something wrong with the Bell test. There's something wrong with the math. I mean, there has to be something wrong.
Well, I mean, what do you think the Bell test is?
It's you're entangling, you're creating an entangled pair, you're sending them far apart to separate detectors that are randomly selecting one of 3 degrees, 0, 120, or 240. And they're registering the measurement, and then later you compare notes, and you see that and then you see that when you measure in the same direction, they're always in opposite spin. So that's good. When when you randomly selected when you randomly select the same direction of measurement, when it was randomly selected, because you use a random selection mechanism, when you randomly select the same direction of measurement, you always get opposite spins. That's the first thing that has to happen. That no one disagrees on. Right?
Mm-hmm.
The question is, what happens when there are different directions? So they're different always by 120 degrees.
Well, they're either up or down. Are you talking about the
The
apparatus?
measurement, yeah, the
thing?
measurement, the
The
measurement.
polarizing filters or
No,
whatever apparatus they're using?
yeah, I mean, yeah, I guess they use the polarizing filters. So, um, so they measure up and down, and according to Einstein, they should get, I mean, altogether 55% different, but in reality, they always measure 50% different. So apparently, quantum. Go ahead.
In the Bell experiment?
That's what I
In the
understand.
Bell test?
Yeah, I mean, that's what I'm actually reviewing Nick from the Science Asylum, his video. So yeah, he says that, and everybody says that Einstein predicted 55%. I mean, it's predicted. If you assume, right, this is all about superposition. So do you assume superposition is epistemic, or is superposition ontologic? So if
You're
you
asking me?
no, I mean, that is what
Oh.
EPR comes to resolve, and that is what Bell comes to resolve, and that is what everybody explained to me thus far. That we're just trying to resolve
Oh.
we're just trying to resolve superposition. Is it epistemic or ontologic?
Well, I don't think that's what the purpose of the EPR paper was. The purpose of the EPR paper was just to show that there's that the model was incomplete, right? Because again, Einstein wanted to hold on to local realism, so they believed that the wave function didn't fully encapsulate what was actually happening on the quantum level. So they wanted to think that there were hidden variables. And so Bell came along and said, well, look, we're going to take some assumptions about, the way that quantum mechanics works.
Hold on.
And we're going to run this test, and we're going to see whether or not, hidden variables and local realism would hold.
Hold
and
on.
They don't hold simultaneously.
Hold on. So you're saying it has nothing to do with superposition? The EPR paper and Bell have nothing to do with superposition?
Well, superposition is sort of like the interpretation of what particles are like when we're not observing them.
But the question is superposition epistemic or ontologic? Right? Is it in our minds or is it in reality? Is right? That is the question is what is the nature of superposition? That was the original question. No? I mean because
Well,
I mean like I'm if you watch my screen share, I'm at the point in Nick the Science Asylum video. That's all he's talking. He's talking about superposition. I mean, he right away takes the side that the particles are showing an essence of upness and downness at the same time. But I think this is what the EPR paper comes to discuss, to resolve.
no, it doesn't. It doesn't resolve anything. The EPR paper doesn't resolve anything. It just like if you like what I posted first
Mm-hmm.
was the conclusion of the paper, which is that the quantum mechanical like there's only one of two things that are possible based off of the mathematics and observations that they did at the time, right? Which were the quantum mechanics, given that it's based off of the wave function, which is this sort of like integral that is done over a probability distribution, et cetera, et cetera. That does not fully describe what's going on at the quantum mechanical level, right? That's one option. The second option is when the operators corresponding to the two physical quantities do not commute, the two quantities cannot have simultaneous reality. Starting when the assumption that the wave function does not give a complete description of the physical reality, we arrived at the conclusion that two physical quantities with non-commuting operators can have simultaneous reality. Thus, the alternative 2, we are thus forced to conclude that the quantum mechanical description of reality given by the wave function is not complete.
I don't really. I mean, I'm trying to like. What I know about the wave function is the way Schrodinger explained it. It just explains how an electron waves around the nucleus. I don't even understand why they bring up the wave function.
Well, the wave function. I mean, the wave function describes, waves writ large. I mean, it's it's like a complex, complex function. But I mean, it's an integral, right? It's an integral over
It's
a probability distribution, right? Given by e to the x squared or whatever.
I mean, e to the x. I mean, e to the x. E to the x.
E to the x
E to
squared.
the ix, whatever, is cosine theta plus or minus I sine theta. If you just take the real part, then that just gives you a wave function, and you can ignore the imaginary part. That's how I understand the wave function. Now, Bohr said that you can square the wave function and get the probability distribution.
Mm-hmm.
Is this what they're talking about? That the probability distribution?
Well, look, you keep bringing up the EPR paper, and I've just pointed out to you just a few times that, like, you said this is what the EPR paper resolves. It doesn't resolve anything. The EPR paper just highlights that there's a paradox, and the paradox just shows that we don't have the full description of quantum mechanical reality, right? Because Einstein at the time wanted to maintain locality, right? Because locality was really important to special relativity, general relativity, and it would just completely, shatter our understanding of reality, because you've got these entities that apparently transfer information faster than light, right?
But they
I
don't
mean, that's
even.
just one interpretation of what's happening,
But
but
they don't even do.
um,
They don't even transfer information faster than light. If you conduct the
I'm not saying they do. That is the concern that Einstein and Rosen and all these
but
people had at
I'm
the time,
saying
was like,
it's worse. If it were that, it would have been nice. It's much worse than that. It's if you conduct the measurements simultaneously, so there's no way for them to communicate, right? They cannot influence each other if you conduct the experiment simultaneously. And even if they do communicate, how does a particle decide? How does it decide how to be measured? That doesn't make any sense. It doesn't have it can't control its orientation. A particle is a dead creature. It doesn't have control, it doesn't have self-control over, and even if it had self-control, it would violate action reaction.
I
It
mean,
would violate.
well, that's not. Yeah, look, it's not about it being a living thing or something like that.
No,
That's
no,
not
no. I'm not saying.
the point.
But it
Like, the
it
point
it
is,
it wouldn't just
whatever's
it
happening,
the particle.
whatever.
No, no, hold on. The particle would have to be intelligent. It would have to have a.
No,
Yeah. I mean,
no,
in order
no,
for
that
this.
no,
No.
no, no, that's not right. Look, what they were concerned about was the theories that they had come up with at the time with special relativity entailed that there was a maximum speed limit that interactions could occur, right? And
Do,
this led to a view of locality,
but
right? The,
do
the
you
way in which
agree? Do you agree with this? With this law of nature,
that
speed of light?
that that the speed of yes, the speed of light
Then how do you
is a fundamental
then how do
constant
you
of nature.
explain then how do you explain this spooky action at a distance, this super telepathy between remote particles? How do you explain it? How do you explain the collusion?
I don't know if it's you or me, but you're cutting out.
Then it's you.
Am I cutting out?
Maybe no, your audio is good, but my audio, there's never an issue with my audio.
I don't know. You're kind of cutting out.
Let me listen to myself on YouTube.
Yeah. Well, the point is, look, with Bell,
Mm-hmm.
right? So what Einstein and all of them were worried about was interactions could not occur faster than the speed of light, right? These interactions that, that happen between quantum particles. So it didn't make sense to them that the results would be, as soon as you measure one particle, the other particle immediately is, up or down.
But what
Right?
if you measure
It didn't make
both
any
at the
sense to
same?
them.
But what if
Okay.
you measure
So
both at the same
so
time?
just let me get through it. Just let me get through it. Right?
Mm-hmm.
Just let me get through it. Okay. So Bell came up with this test because Einstein really wanted to hold on to locality, and in order to do that, they posited that there were some hidden variables, right? And that's why they're saying that the wave function is not a complete description of quantum mechanical phenomena, right? So Bell came up with this test, right? And then many years later, people actually conducted the test,
Mm-hmm.
and the results were that it defied the Bell inequality, right? What you would have if it were the case that there were hidden variables affecting, the behavior of these particles. The inequality came out in such a way that it just basically proved that you could have either, well, including statistical independence, but you could have either hidden variables but no locality, or you could have locality but no hidden variables, right? Or you could have neither, right? But you couldn't have both.
I don't know what that means.
Locality meaning like
Locality,
interactions can only occur
right?
within
Locally,
the speed of light.
yeah. hmm
Hidden variables meaning there are things that we're just not able to measure. Right? So like Bohmian mechanics posits, like with pilot wave theory, that there are hidden variables, but they're like non-local, and the non-locality is just like, the initial relative conditions of the state or something like that.
Wait, let me send you a friend request because you're like 1 in 1 billion. How do you know so much?
Just read.
Jesus Christ.
What does he know?
A little bit.
You just read. The elements of the physical reality cannot be determined by the prior physical expectation.
So you're saying okay, you agree that there is a paradox, right, Mr. Good Boy? You agree that the EPR paper
EPR.
presents a paradox.
I mean, if you're to accept local hidden variable theories, yes.
No, if you assume locality and realism, if you assume
And
realism,
hidden variables.
no, let's not assume hidden variables.
Well, that's what the paradox relies on.
That's the resolution to the paradox.
Well, in order for it to be a paradox with the information that we have now, it would have to be a hidden variable theory, a local hidden variable theory.
No, before the theory, first
Not
let's
just-
present the paradox. The EPR paradox, right? There is an EPR paradox.
Okay.
Right, the EPR paradox doesn't offer a solution. It just offers a paradox, a contradiction. So based on these assumptions, we have a contradiction. So the assumption is realism and locality. And entangled states always give opposite spin measurements, even when far apart, simultaneously.
Mm-hmm. Yeah.
So they seem to be communicating faster than light, which is right, that violates the assumption, hence a paradox.
Yeah, I mean, they have to have some sort of interaction. Yes, that occurs faster than light. But
that's
one
explanation.
Like,
so
I know
there's two explanations.
Yeah.
Right? Either if you assume superposition is ontologic, then you need to resolve the paradox. But if you assume superposition is epistemic, then the paradox doesn't lift off the ground. Right? If you assume superposition is epistemic, then there is no paradox. The paradox is only created if you assume superposition is ontologic.
Assume superposition. No. What? I don't understand what you're saying. Like, look.
Superposition is either.
The point is.
It's either that the particle. It's either the cat is both dead and alive. That's ontologic, or the cat is either dead or alive. That's epistemic. So what do you think? Is the cat both dead and alive, or either dead and alive? Dead or alive?
Well, look, you'd have to show that.
Isn't this what this paper comes to resolve? Isn't
No,
this
you
the
said that like multiple times, and I've shown you the text where it explicitly doesn't resolve that.
I can't understand the text. I wish I could understand it. I mean, you read it like it makes sense. I read it, it literally makes no sense. I cannot get through the first. I don't even understand the
All it said,
title.
look, well, I don't. What do you mean you don't understand the title? This is the paper you're purporting to cite, and I'm citing it for you, and I'm telling you it
I
says,
agree.
like word for word, word for word,
Yeah.
it says, we are thus forced to conclude that the quantum mechanical description of physical reality given by the wave function is not complete. That's the conclusion
I don't know what that
of the
means.
paper. It it means that they have an assumption that they're working off of, which is the wave function, right? That is like the crux of quantum mechanics, right?
Why is that the crux of quantum
Do you agree with that?
mechanics? Why is that the crux of
Because
quantum mechanics?
what do you
Why
mean that? Why is that? That
why
that's
isn't
that is the
Planck
foundation. That's one
why
of
isn't
that's at least one of the found.
I mean there's many
What?
foundations to quantum mechanics. One of them is the wave function. The wave function also explains how strings vibrate. It's just we notice that elementary particles are waves. Hence, we use the wave function to describe their motion because we notice that they wave. We notice that light is
Yes,
a wave. We notice that
yes,
electrons.
and so
Mhm.
yes, and so given that it is foundational to quantum mechanics, and you have this paradox that arises because of it, right? Then you have to conclude that
What's the wait?
this
Wait. What's
this that
there's
this
wait wait
that
wait
this that this foundation
wait. Hold
is
on.
incomplete.
Hold on. So we notice that electrons and light, and then later on neutrons, and later on basically everything behaves like a wave. But let's start with even a photon. We discovered that long ago that photons behave like waves. Okay, so you could say it's foundational that elementary particles are really elementary waves, and therefore
Okay.
the wave function describes them. That's fine. And you could say that's
Yeah.
elementary, that's foundational. But
All right.
because they are waves, we have a paradox. Why
The,
would I care?
the paradox is as we described, right? Which is that you measure the outcome, like the spin of one particle, and that tells you exactly what the spin of the other
But
particle
how is
is.
that different than two socks? That I measure one sock is the right sock, immediately I know what's on the other foot, or what's on the other side of the visible universe. If I put two socks in two separate boxes, right sock and left sock, so as soon as I open the box on one side of the universe, I know it's epistemic. Why should I? And I'm right. As soon as if I define superposition to be epistemic, I don't have a paradox. It's only if I define superposition to be ontologic that I have a paradox. Because then, how do the two particles commune or communicate in order to be measured in a correlated way? Then you have a paradox. You don't have a paradox if you define superposition to be epistemic, right?
No, I think it's been pretty well established that like the states of these particles is inherently random. Like it's not some misunderstanding that we have about them.
No, Einstein and Schrodinger. Schrodinger came up with the cat thought experiment. Schrodinger's cat. I mean, I think the EPR paper is just an extension of Schrodinger's cat. It's just a way to measure Schrodinger's cat. And Schrodinger's cat is the fact that Schrodinger and Einstein, they were friends, and we have their correspondence that Schrodinger, when he came up with the cat thought experiment, he told it to Einstein, and they laughed about it and they loved it, but it was incomplete because it's just a thought experiment, and people still believe, yeah, the cat is both dead and alive. So then Einstein came up with the EPR paper, and he wrote to Schrodinger about it, and Schrodinger said, "Wow, beautiful, you did it this time. They're not getting away this time."
Who's not getting away from what?
Bohr and Heisenberg, from believing that the cat is both dead and alive, that superposition is ontologic. This time we have them. And everyone went to their graves believing that that EPR won. EPR and Schrodinger won the discussion. The discussion is over. Because a paradox,
I don't know what you're talking about.
if you assume this paper, EPR assumes, for the benefit of Bohr, EPR paper assumes Bohr's position that superposition is ontologic. So then you get this paradox. That's it. That's the end of it. Therefore, you cannot say superposition is ontologic. It must be epistemic. That's why I keep saying that's the purpose of this paper. It presents a paradox. It seals the deal. They're not getting away this time is basically what Schrodinger wrote back to Einstein. You did it this time. That's it. They're not getting away this time. And they didn't get away. Everybody died. And then Bell, after everybody died, Bell came up with his test. But Einstein went to his grave long after this has been settled in his mind. Einstein thought it's settled. No one ever responded to the EPR paper. I mean, maybe Bohr responded to
A
it.
lot of
Mhm.
What do you mean? A lot of people responded to it, but like again, what is there to respond to other than to come up with either hidden local variable theories or hidden variable theories
But that's
that are
only
non-local,
if you
or just
assume.
non-local theories.
Only if you assume the EPR paper is written only for the people that assume that superposition is ontologic. If superposition is assumed
That's
to be,
nowhere in the paper. What you're saying is nowhere in the paper.
but we have the
Can you point out to me?
correspondence. That
Can you point out to me?
the correspondence, so we know. Look, I don't know anything. I mean, I can look it up. Maybe I'll find it. I mean,
You're gonna have to post, like, cite what you're talking about. I don't, because as far as I know, it's been pretty well established that unless you have some other formal inference model, right, about quantum mechanics, which some people are trying to develop, right, which would essentially sort of clear up this sort of like these sort of issues, right? But that has yet to happen, right? You take into account all of the logical inference models, right? Including
okay, here, listen. So
formal logic. Excuse me. Hold on. Just wait. Okay. Including formal logic, classical logic. You can take into account intuitionistic logic, constructivism, etc. You're going to come up with the same results because the measurements show that this is not a failing of our understanding, right? This is like there is something missing from the model, right? The model is describing accurately what's happening, but we're missing something from it that would encompass the explanation as to why things like entanglement happen and why Bell inequalities happen. But you have to give an actual inference model. You can't just like say it's epistemological. No, that doesn't do anything. That doesn't say anything. And that's not what Einstein and Rosen said, right? They said that this is a serious issue. This is like, we take quantum mechanics seriously. We think that the wave function describes what's going on. However, it's incomplete because of this paradox.
hold on.
And we think that future models are going to provide for hidden variables.
I honestly don't understand. But here is I did a Brave search, which is an AI. So Schrodinger's response to EPR. Schrodinger wrote to Einstein after the publication of the EPR paper, mentioning that he thought the paper was great. However, the details of Schrodinger's exact words are not provided in available information. It is known that Schrodinger and Einstein exchanged letters about the EPR article, with Einstein pointing out that the counterintuitive nature of quantum superposition, with Einstein pointing out that the counterintuitive nature of quantum superpositions. Schrodinger responded with his famous thought experiment, Schrodinger's cat, to illustrate the problems of the Copenhagen interpretation of quantum mechanics. So I guess it happened after. I guess
Yeah, I mean, Schrodinger's cat was, a thought experiment that was supposed to show the absurdity of superpositions, and that's fine, right? But that just goes to show it's the same sort of thing that Einstein was saying in his paper, which is even though the wave function accurately describes, and it accurately describes what's happening at the quantum mechanical level, a consequence of it is this paradox, or Schrodinger's cat, for example, Schrodinger's cat thought experiment, right? You can come up with these things that are very counterintuitive and probably don't even happen really, right? But there's no answer to those questions just yet. Like, why is it that these particles now? Leonard Susskind does have a ePR that responds directly to this.
EPR equals
ER equals EPR, right?
Yeah, that's nonsense. Yeah. That's obviously complete. Everybody's going off the deep end. This is why I'm trying to stop it before everybody. Like, I don't care what Susskind. I love Susskind, but obviously that's utter nonsense.
Come on, bro. You're like admitting to me you don't understand the EPR paper, and you're gonna tell me that like you think Leonard Susskind is going off the deep end because they're positing like wormholes or something.
Wormholes are
like
wormholes is nonsense. It doesn't make.
How is that? How is it nonsense?
Because there's no singularity at the center of a black hole.
What does that have to do with? What does that have to do with the wormhole? I mean, how would that even show that wormholes? Saying like there's no singularity at the center of a black hole.
So there's nothing special.
No such thing as a wormhole.
What do you mean? There's nothing special. There's nothing special in a black hole. Black hole is no different than the Earth, or you and me, or an electron, or a photon. There's nothing special. There's nothing special about it. If there's no singularity, if there is no singularity, then how is it suddenly connected through a wormhole to another part of the universe?
Well, black holes are clearly different than like other physical objects in the universe.
No.
Like they're very different than stars. They're very different than
not really
like planets.
No, I don't.
Yes, they. How are they not different?
It's just that the curvature. The curvature around, at the event horizon reaches the speed of light. That's all. There's nothing special about it.
It exceeds the speed of light.
I mean, the event horizon is where it reaches the speed of light.
Light cannot escape it.
Yeah, fine. So what? Light cannot escape the cosmic horizon. Light cannot escape. If I move at 90% the speed of light to the right, and you move at 90% of the speed of light to the left, me sending you a beam of light will never reach you. So what? Who cares? That's boring. There's nothing special about that.
What do you mean it's boring? Like,
there's nothing. There's no wormhole.
So you're not interested in it.
No, I'm
why does that?
I just bring it.
Obviously, physicists are very interested in what happens at the horizon of a black hole, and and within a black hole,
Yeah, I'm
right?
very
And the jury's
interested.
out
I'm
as to
very,
whether or not
I'm very,
there's a singularity.
I'm very interested. To me, there, right? To me, I don't have an issue with any. I never had an issue with black holes. I never believed in singularities. I never had a problem with the event horizon. And so there's no room for me. Like the Penrose diagram to me is also nonsensical. I mean, it's convenient a little bit, but once you turn it into a multiverse, it's not. It's nonsense. I mean, the wormhole is nonsense. Anyway. Look, so
I don't know how you can speak so confidently saying like these things are nonsense. Like these are hypothetical models, right?
they're
That would
not.
resolve these problems.
These
Yes, they are.
they're not, because they're look. It's not that I'm saying they're nonsensical. It's that they say it's nonsensical. Like when you say when you
Who
s-
says it's nonsensical?
when you say that you broke reality here. So Nick from the Science Asylum, how entanglement breaks the universe. So, right, according to you, according to Nick, entanglement is nonsensical. What does it mean to break the universe? It's nonsensical. So everybody agrees that it's nonsensical. That it doesn't make any sense. It's illogical. It doesn't like it. They cannot make sense of it. Everybody agrees that they cannot make sense of entanglement. Everybody agrees. Everybody agrees that Bell's theorem drives them insane. Everybody agrees.
It doesn't drive them insane. But it just drives them to come up with theories
To
that are
say
not either non-local or they don't
non-local,
have hidden variables.
look, non-local would be fine if you would discover somehow that you can violate the speed of light, which is ridiculous because we've tried violating the speed of light in particle accelerators. And as we get close to the speed of light, particles reach infinite momentum and we cannot accelerate them past the speed of light if they have mass. And if they don't have mass, we can't accelerate light beyond the speed of light. And gravitation seems to be also traveling at the speed of light. So there seems to be a cosmic speed limit that no one has ever witnessed we can breach. So there seems to be a law of nature that we've never been able to breach, that is the speed of light. So for you
Yeah, but
to
a theory being non-local does
that
not
would be
inherently
fine.
mean that
I don't if
it
you
exceeds the speed of
eh,
light.
that's fine. If you can exceed the speed of light and you discover I can travel at warp 2, 10, 20, 100,
Are,
1,000, that's
are you
fine.
listening to what I'm saying?
What?
Are you
Repeat.
listening to what I'm saying?
Repeat, please.
Like, okay, as I said, a theory being non-local does not imply inherently that that means that the mechanics of the theory break the speed of light. Like Bohmian mechanics is a non-local theory. It doesn't violate any superluminal speeds.
There is a guy, Sutter. You know the physicist? He has a podcast. Sutter?
No.
So he went through all the interpretations. He showed that every quantum mechanical interpretation is incomplete. Copenhagen, multiverse, Bohm mechanics. He goes through each one. He showed that each one is nonsensical. It doesn't make any sense at one point, at least at one point.
Like he's showing contradictions or what?
Like he said, what is the collapse of the wave function, right? No one understands why, what exactly is this collapse? What is this measurement? What is this observer? No one has an answer to this, right? This is a known problem.
That's not an argument.
I mean,
It's not an argument against a model.
no, I
It's
mean,
like that's an argument from ignorance.
okay, fine. So he shows that it's incomplete. Fine. He shows that every quantum model.
You mean like the EPR paper does? Like every
I
physicist
don't
understands already?
I don't understand the EPR paper, but he went through every famous multiple quantum interpretations, and he showed that each one is incomplete. We are ignorant about at least one aspect.
So what?
So Bohmian mechanics, you're not going to get away with Bohmian mechanics. You're not going to get away with ER equals EPR. You're not going to get away with anything except for you're going to have to struggle and explain how Bell is wrong. If you can explain that Bell is wrong, you fix the universe. Bell must be wrong.
I mean, have they shown that? 'Cause it doesn't sound like they have.
That's what I'm trying to show. So I wrote a script that in the script I was basically getting the 55%. The famous 55. Do you know the 55 versus 50%?
No.
Einstein predicts 55% up versus down. You never heard of this? Like, I mean, that is Bell's test. That according to Einstein, it is predicted 50% is predicted. 55% is predicted according to Einstein. But in the tests, this is what the Nobel Prize is all about. That if you assume superposition is epistemic, then you predict 55% up versus down. But in reality, when we run the test, we get 50% up versus down, which is what Nick from the Science Asylum. Do you know Nick from Science Asylum?
No.
You don't watch YouTube?
Sometimes.
You've never watched the Science Asylum?
No.
Anyway.
I mean, maybe, I don't.
Okay.
But it doesn't sound familiar.
Okay. Okay. So he says that, and he shows. I didn't go through the proof. He has a proof that from quantum mechanics, using the Dirac notation.
Listen, can I prove that your mom's a spiritual whore? It's a yes or no question, man.
Let me just mute this guy.
Yeah.
Yeah, I debated him yesterday, I think, about something. He went off the deep end. I think I debated him about God. Oh, about heaven and heaven and hell. I told him that even if everything he's saying about God is correct, then I'm not going to submit to his God. And he got really upset.
Mm-hmm.
Anyway, so they say that if you assume superposition is epistemic, right? I mean, that is Bell's, right? The prediction of, right, when you go through the predictions of Bell's test, right? If you go
I'm
through,
looking at this.
what?
I'm looking at this Science Asylum thing.
Okay, let me give you the link.
I don't know if this is the same guy you're talking about, but he's going through the same possibilities that I described earlier, which are like.
Yeah, I'm not saying that you're wrong. You're saying basically what everybody else is saying. I'm not complaining.
Probability of 5/9. Or 55.6.
I appreciate the time that you're that you're spending trying to explain this to me. That I really appreciate. Let me just
6%.
That's stuck. Anyway, so he gets 55.6%.
Well, so yeah, this was the video that I was watching. You might be interested in watching someone named
Brian Green.
Rob Specken.
Rob Specken?
No. Rob Speckens. So Rob Speckens is a proponent of building a new interpretation of quantum mechanics based off of a different sort of like formal inference system. Now, I don't know exactly what his inference system is. I don't even know if he's published it yet, but essentially he's kind of saying something similar to what you're saying, which is there are issues with the way that we make inferences about quantum mechanical systems, and we just need to have a different sort of formal system to describe those things. And a lot of these issues, like entanglement, really aren't the problems we make them out to be, right? And that's what I was trying to tell you earlier. But I think he's still in the same standing as any other person who has a hypothetical model. Like, I think he's in the same standing as Leonard Susskind when Leonard Susskind says ER equals EPR, or Penrose, who has his diagrams, or whatever other shit is out there, like string theory or whatever. Like, these are all on the same level to me, or Bohmian mechanics for that matter. Like, I don't think that the question is it something that, like, are there actual faster than light interactions that are occurring, or is it something that we're just missing from our model? That's a fine debate to have, but I think the answer just is not going to be readily available at this point in time. I mean,
I mean, look, I wrote a script, so I don't like I didn't go through the mathematical proofs. I just wrote a script. Do you understand like Python, simple Python?
I'm not a computer programmer, but I mean, you can post.
I can
like
share
the gist of what you did. Yeah.
I can share. I think this is the best link. Share. Anyone copy? But you can also watch my stream, but then you would get a feedback. But maybe the best thing is to watch my stream so I can show it to you.
Well, I'm about to go to bed, so.
Okay, so let's do this. I gotta run to the bathroom because I'm about to poop my pants. Okay, I sent you a friend request.
Okay.
Did you get it?
Yeah, I think so.
Can you approve it, please, if you don't mind?
Yeah. I just posted Rob Speckens.
Yeah. I
video.
I already
so.
searched him, so I'm gonna watch him next. So I'll be in touch with you because you're awesome. You're unbelievable. You're like a international treasure. You're a cosmic scale treasure.
Wow.
Wait, you're a vegan?
Well, I appreciate it. No.
Why are you on Ask Yourself? Why are you a bad boy on Ask Yourself? Because you're not a vegan?
Well, I don't know.
That's
I
fine.
guess. Is that my name on
It
on there.
says bad boy under when I look at your profile. It just you can see
Oh,
it
I see.
too.
Yeah, somebody probably changed my name. I don't know.
Yeah, they changed my name too. All right, I'm gonna stay in touch with you because you're awesome. And
All right, I appreciate it.
we need to talk about a lot of stuff because like we just touched on one thing, but I need to talk to you about everything. Like I have so much stuff to share with you if you'd like. Anyway,
All right.
thank you so much, and I'll catch you later, man.
Yep.
All right, bye.
Have a good one.
You too, bye.
Bye.
All right, that was awesome. Absolutely awesome. Wow, this guy's like next level. That was incredible. Okay, let me go take a break and then we'll see what's up. Wait. Let's take this before the room shuts down.
That's detrimental to progress, I would say.
Okay, we'll come back to this. Anything else critical? No. All right. All right. Let me post this on my server. Where's my server? I guess in general we can paste it. Lee, 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 la, la. All right, we're done. Let me run to the bathroom and maybe eat something. Bye for now. Wait, what's going on? What is going on? Oh, Brave is stuck. That's good. Snipping tool is reacting. What is going on here? Mm-hmm. Okay, bye.